So hi guys, to recap everything we discussed so far, .NET provides us thread pool that we can get threads from to reuse for our work. We can chain tasks with async await. We should strive to never block the thread in case of input-output operation. We also discussed synchronization primitives to synchronize between threads using semaphore slim for asynchronous work or just primitive log for synchronous work. We looked at some thread-safe collections at producer-consumer model, namely blocking collection for synchronous work and channels for asynchronous work. We looked at parallel and plain queue, and also at asynchronous streams. Today is about more advanced tips and techniques and also about performance optimizations. However, I wanted to start today's meetup with finishing discussion on multiple different topics that we didn't cover during all the previous 5 meetups. I had them marked for future so that we can finish all the topics before delving deep into advanced stuff. So let's start with async configure await discussion. Like remember, we need if we're writing some library code and we're not sure where our code will be executed, we need to call configure await false everywhere on every await in order not to introduce any deadlocks, because if our code runs on some custom synchronization context, then it will deadlock if somebody tries to block on this async operation. Well, there is a very cool feature that was added in .NET 8. So in the latest .NET, currently we have another overload here in configure await. Instead of just passing false, we can pass configure await options, which has some additional parameters. So none is the same as configure await false. So it will not capture the context. So if you want to make sure that you are writing correct code in your libraries, you can just use configure await options none instead of false. Continual captured context is the same as true, so it will capture the context. This is where things get interesting. We get additional option, for example, force yielding, and also suppress throwing. So what does force yielding do? Force yielding, it forces to yield this execution to thread pool, the same way that task yield returns an incomplete task that will be completed as soon as it is scheduled to run in the thread pool. So this ensures that the rest of the method will be executed by some other background thread. However, if you use task yield always captures the context. So there is no possibility to actually call configure await false here. It will always capture the context, unfortunately. And force yielding is the same as calling task yield, but with configure await false. So it will also not capture any context. In fact, some people like Steven Taub, core developer of Microsoft, of this all this async stuff, they started instead of doing this, in order to run some task on the background thread, they started doing this. And it will do essentially the same thing, except it will not create a new task and it will not delegate it on a thread, on a heap and it will not needed to be garbage collected. So this thing is more optimized than this thing. Another option that we have here is suppress throwing. It's useful when you do not care about the result of the task and you want it to just complete. And you have some code inside that might throw exceptions, but you do not care about it. Then you can use suppress throwing option instead of using try catch around your call to some asynchronous method, and it will not throw any exceptions. With one caveat, obviously this thing works only on tasks that do not produce any results, because the task that produce some results, it needs to return some result. So if you call this on tasks that has some generic parameter, like a type of result, it will throw an exception saying that it's not supported. Another thing that I wanted to highlight is that configure await works on the awaitable and not on the task. And what it means that if you write something like this, configure await doesn't do here anything, because configure await returns an awaitable. You need to either store this awaitable somewhere and await an awaitable, or you need to await an awaitable here. So you need to add configure await here. You can just call it on a task and expect this task later to not capture the context. This task will capture the context. Configure await creates for you an awaitable that you can await and not capture the context. And obviously, if task is already completed, await checks it and executes all the rest of the code in the same thread that await has been called from. So configure await also will not do anything in this case. So it will not do anything if task has already completed. Now, if you have some task and you do not care about the result and you do not want to await it, you want it to be executed in the background, you can always just do it like this, right? And it will just run in the background. This construction creates a new task and it will just run in background. In the same way, you can just call some methods that return task and it will just run in background. .NET saves all the references to all the tasks that are not completed yet to some static class, so they will never be disposed and your operation will never stop executing. So you can run some even long-running operations in this way. However, as you may notice, Visual Studio produces a warning that because this call is not awaited, execution will continue. How we can make it all beautiful and not produce this warning? We can always assign it to a variable. But then if we do not use this variable anywhere, then we get a warning that remove unused local variable. So what we can do instead is we can use a discard operator like this. This basically shows our intent in the code. We are telling that we do not care about the result. We just assign it to discard, so it cannot be used at any point later. And this operation will be executed in the background without awaiting it. Discard operators can be used multiple times. It's a new language feature, relatively new. So it can be used not just for tasks, but for anything else you want to use it. But this is just the case how we can beautifully run the task in the background. About disposables, jump into disposables. So .NET has a disposable interface in order to dispose from all managed or unmanaged resources that we need to dispose of, right? Well, with some version, .NET introduced also iAsync disposable interface that basically has one method, a dispose async that returns value task. You can have it async, you can await any operations inside if you need to. So if you need to have asynchronous disposable flow, you can just use iAsync disposable instead of iDisposable and create dispose async method. Later, when you need to use it, you can either call manually dispose async on that instance, or you can use construction await using instead of just using. However, here's a caveat. If you need to call configure await on this disposable, then you cannot call it easily, because if you call it just here, configure await false, then this instance will not be the instance of your class. It will be the instance of an awaitable. So in order to call configure await, we need to either do this, assign it to a variable, and then use await using with configure await. But then if you go outside of the scope, here your code can access this variable that is already disposed, so which is not very good. Another option is we can just call dispose manually using try finally block, old-fashioned way. But again, here our code can access instance variable. Another option, probably the best, is we can use scopeless using await using block without any curly brackets, which will mean that your instance will be disposed as soon as we go out of scope. This way, your code can access the instance variable, but as soon as we go out of scope, you can neither access instance variable, and it is also being disposed here. Now about constructors. What if you needed to create an object and you wanted to create it asynchronously? So you need to run some asynchronous code in the constructor. Well, if you just create a public constructor and you create a separate method like initialize async, this breaks encapsulation, because now you need to, from some other point of code, you need to not forget to call initialize method, etc. A better option would be to use a async factory method pattern. So you create a private constructor, passing all the data that you need inside the constructor. This is a workaround because constructors cannot be asynchronous. And you create a public async static method, create async, that returns you an instance of your class where you do all your asynchronous work, and then you construct and return your object instance. This way, whenever you need to create your object, you can just use this method, passing all the variables that you need into it, and it will return you already initialized instance, assuming you awaited, of course. All right. One more thing about locking. We discussed that we cannot use this lock in async code. Why is that? This monitor exit method, it expects to be called from the same thread where you call monitor enter method. But if you have asynchronous code, then any await here inside, it might execute its continuation, including the finally block, on the different thread. So if monitor exit happens on the different thread than monitor enter, you will get a runtime error exception thrown that it cannot be unlocked. And this code will not even compile. Compiler will see that the method is asynchronous and will not let you use this construction. Also about all the mutexes, semaphores, and semaphore slim, all these constructions also disposable. So do not forget to call dispose on them if you use them somewhere in your class in dispose method. And about PlinQ, one more thing. Yeah, jumping all around. Not PlinQ. PlinQ cannot be asynchronous, but parallel for. Parallel for each, and parallel invoke that allows us to run some operations. Starting from .NET 6, they also have additional methods for async, for each async, and invoke async. So you can run some asynchronous delegates here. For example, if you have IO-bound work, you can run parallel for async and like 1000 asynchronous operations without any issues and blocking any threads. No. Now let's move on to our performance optimization chapter. We'll start with performance optimization. First thing I wanted to discuss is how the task is created. Whenever the task is created, so you have some await async method, or you create task using await async method, the task is created for you. For example, first of all, the task is a class, so it needs to be allocated on the heap. And so later, when garbage collection occurs, it also needs to collect it. So if you create 10 tasks later need to be collected. Furthermore, whenever you have asynchronous method, like I showed you before, a state machine needs to be created. State machine is a separate class that provides for us this behavior of chaining tasks after every await. So this state machine is also a class, and it also needs to be allocated on the heap. Execution context, that is just there, like I told, and we do not need to even to think about it. It just allows us to use, for example, async local. Execution context also is a structure or a class that needs to be allocated and copied down to the next task. And also, if we pass any variables into our task, like we pass a delegate that uses some variables, then these variables, for example, this one, they need to be assigned to some member values of a new class that is called a closure. And this closure needs to also be allocated in order for this delegate to be able to use this variable later on. So at least 4 allocations are happening every time we create a task. And if we have some method that are calling another method that is calling another method, and all of them async awaits, and they all await each other, then it will all multiply by 4. All the allocations that we need to create, and then we need to dispose of them. Like, I mean, the garbage collection, whenever it occurs, it needs to dispose of all these resources. However, hear me out here. Everything I told so far is related to the old .NET, and maybe even the first .NET Core, or maybe even the third .NET Core. I'm not sure exactly, but probably just all .NET. In recent work, every .NET Core has improved significantly the performance of all these asynchronous primitives. So at least saying about .NET 6 or even .NET 8, I can tell you that only one allocation happens for every task, the task itself. Because all the other constructions that needed to be allocated, they are either merged into the task or they are made static, or some other optimization have been made during a JIT compilation. The thing is that it greatly improved performance of all our async work. And if in the old .NET running millions of methods produced in one of the tests 200 megabytes of allocated objects, in .NET Core it produced with the same test just 100 kilobytes of allocated objects. So it's more than 2000 times smaller footprint. However, the task itself, allocation, still happens because task is a class. But we do not always need to allocate tasks, right? Sometimes we just return synchronous result. Sometimes no awaits are happening inside. Sometimes it just throws an exception. Every time such synchronous operation happens, we still create a new task. because we are returning the task. What if we could completely remove that allocation? Completely make our code allocation free whenever we have asynchronous code. This is what value task tries to achieve. Value task is a new construction added to .NET Core, which is not a class. It's a struct. So it is not being allocated on the heap, it is being allocated on the stack. It doesn't need to be garbage collected later, and performance is much improved. Now, the differences between tasks and value tasks. What are the caveats? If it's so great, why not use it everywhere, right? Well, from implementer point of view, whenever we need to implement our asynchronous method, we can just change task to value tasks and leave async await as is. The magic will happen for us. So if we have some synchronous logic inside and it threw an exception or it returned the value before any of the awaits happened, then value task will just return you this value and no allocations will happen. If, however, you await some task that returns tasks, some method that return tasks or some task inside, then value task will just wrap around this task and internally it will use the task for synchronous operation and then it will return you a value. So one main distinction between tasks and value tasks is you cannot await value tasks multiple times and you cannot block on them. This is the main caveat of value tasks. So value tasks were created from the point of view that we have a lot of methods from our repositories, from API endpoints, from every other library. They all have async methods. And we are usually calling them like this. We just call the methods and we just await it instantly and assign it to some variable. So this is the proper use of value tasks. Value tasks should always be used like this. In perfectly, you want to await it as soon as you call the method, and you do not want to even assign it to a variable. In fact, if you assign to a variable this task without awaiting it, the .NET will generate you a warning. Well, it doesn't generate for me, but I guess I configured it in a different way. It will usually generate you a warning that value tasks should not be assigned to a variable because there is a risk that you will try to access it as a result from this value task, or you will try to await it multiple times. So yeah, it's because this method is not await. That's why it doesn't work. Thing is that if you await it multiple times, the behavior is not determined at all, like it's written in Microsoft documentation. What it means is that it is completely dependent on the internal implementation of this specific value task generator. Well, you can await general tasks multiple times and you can get this result. You cannot do the same with value tasks. If you just want to have a method and you want to await it, then yeah, go ahead and convert it from task to value tasks. There are two groups of people. One thinks that value tasks needs to be used only whenever you want to have some optimization and you carefully consider that it is really needed there. Another group of people think that we should change all the tasks into value tasks wherever possible, always. Well, to be honest, I think that I belong to the second group of people. I have been using value tasks wherever I could because it brings you the benefits always. And if you want to await the value task multiple times, or you want to get its result even before it completed, you can always use method as_task on the value tasks. It's a bit of an overhead, but it returns you a task instance from this value task. If the result was successful, it returns you a task from result. If exception, task from exception. If the result is not completed yet, it returns you the underlying task that is performing a synchronous operation right now. And then you can await it multiple times. You can get its result. So yeah, in this case, we do not need await here, and we can see that there are like different properties of task here. So we can block on it, for example. However, if you just have a lot of methods and every method calls another method, especially on hot path, then value task will benefit us greatly, potentially, again. In order to reduce all the allocations and return results synchronously whenever we can return them synchronously. This is an example of value task. So we have some methods where we just await something, and then we await some other method. And this some other method also returns value tasks, just returns string. However, as you can see, it only awaits every other second. So 1 second it will await, and another second it will just return hello. And whenever this hello is returned, it is returned without any allocations of task objects on the heap. It is just returned by value. Yeah, well, this is a result of a cache. So you have some cache and you have some invalidation conditions there, and on invalidation condition you get the value using asynchronous code, but until invalidation occurs, you just return cached value. So this cached value is returned without allocating any tasks. Value task also have methods from exception, from result, from cancelled, same as task. And if you have some method like this, by the way, this is a method of, this is an example of method without async keyword. So this is a method that returns value task instance without async await. So here, for example, you can create a task, and you can create a new value task and wrap it around task. So value task accepts a task as one of its overloads, which will return you a new value task with this underlying task. However, if you have just some synchronous result, you can just return value task with this result directly without any tasks at all. Since it's a structure, you can also return default. So whenever you want to return a value task without any result, just an empty value task. Why we cannot await it multiple times or get its result before the value task is completed? It's because value tasks are internally pulled. So there is some mechanism to run value task. It's a complex mechanism. And it gets pulled into a pool of value tasks. So you can have one value task, and it might be used for completely different operations. So if you await it the second time, it's not guaranteed that that like your that it will run on your operation, something like this. Yeah, it's difficult to explain. Let me just show you what is value task in essence. So value tasks can be wrapped around just a regular task. In this case, they just encapsulate in task operation. However, a pure value tasks might not even use tasks at all. They might be asynchronous, completely asynchronous, but at the same time, they will not allocate anything and they will not use value tasks. This can be achieved using iValue task source interface. iValue task source interface allows you to create a value task source from which you create new value tasks. And this iValue tasks source, it has three methods: get result, which gets current result; get status, that gets current status; and on completed, that runs continuation on completion. The implementation of the value task is rather complex. It takes like 500 or more lines of code in Microsoft reference implementation, so I did not even delve into trying to create it. I read a bit, but then I gave up. So you should generally not attempt to create your own value task sources wherever you want to use that cool feature of pooling value tasks. However, .NET provided for us a special async method builder. By marking our method with this async method builder, type of pooling async value task method builder, we are essentially telling .NET compiler to generate this method in a different way. It will attempt to generate this method not using this task as a task, but it will attempt to generate this method using pooling behavior of value tasks. From the tests that Microsoft internally performed, they ran billions of operations to really see the results. So they ran a lot of value tasks. Without this async method builder, it generated, because tasks are still allocated, it generated 11 gigabytes of allocations. But with this attribute added, it generated just 200 kilobytes. So pretty much zero. We can assume that it's zero allocations. However, there are some caveats, of course, using it. I'm not using it anywhere in my code. It has some pitfalls. First of all, there might be a slightly less performance here because pooling also incurs some additional overhead. So it conserves memory, but it incurs performance issues. So consider whether you really need to conserve memory. Second of all, you cannot await it multiple times, like I told before. Well, you shouldn't attempt to await any value task twice, but if value task is backed with just regular task, you might be able to await it multiple times. Not can, but might be. With this attribute added to the method, you will not be able to await it multiple times for sure, because it is now a pooled value task. It is returned to the pool as soon as you await it, after it completes. Yeah, this is pretty much everything about value tasks. Let's switch to the other performance tips. So first of all, of course, execution context, it doesn't impact anything at all, and the performance gains are negligible, so you shouldn't really do it anytime. But in case you are designing games or something where you need every nanosecond to count, you can suppress execution context flow. Your async locals will not work then, but at least it might improve some performance a bit, because you will not flow the execution context from one task to another. Now, another thing, another cool feature that we have in .NET 6 is wait async. Wait async is a method on a task. So remember, we had linked cancellation token sources to cancel the task after some time. Well, we can cancel any task. I mean, not cancel, but we can wait for any task with this magic method wait any for some specific time. So this method will either stop executing in 5 seconds until you get to the next line. Well, the task itself will continue executing, but at least you will not be stuck here forever. Or if the task completes earlier than these 5 seconds, then you are just also of course, passing to the next line. So this is just a shorthand, a very cool syntactic thing to instead of create our own extensions for that, we can just use it starting from .NET 6. One more optimization that we can make is, of course, removing async await from our code. So if we see that we just returned from the client something, right, async, and this is task HTTP response message, so it's the same type as we are returning from our method. We also return here task HTTP response message. So then why use async await? We can just remove them. So we can do this optimization. However, be mindful that if you use, for example, a using block, then this will break your code, this optimization. Because previously we were creating a new resource, we were waiting until this operation completes, and then we were disposing this object. If we remove async await, then we are creating a new disposable resource. We return from this method not completed yet task that will query this URL. And as soon as we return it, we dispose of this object. So later, whenever somebody tries to access the result of this method and read something from it, like here, task wait and then task, this thing will throw an exception because this task internally will try to send something to this URL and it will try to use HTTP client, but it will already be disposed by this moment of time. Same issue happens if you have try catch block. So imagine you have catch that you're catching some specific exception here. If you have async await, then you're catching the exception from using that method. So if that method throws an exception, you're catching it here and you are somehow handling it. If you remove async await, then you are just returning immediately a new task that has not even begun executing yet, and this code will never be executed. Yeah, so whenever doing the optimization of removing async await, do it carefully. Make sure that there are no side effects like this. One more optimization that we can use is use this method. So remember, we have a method that will work on the thread pool queue user work item. It will crash your host if any exception happens inside your method, unfortunately, compared to tasks. But it is slightly faster, of course, because you do not allocate tasks, you do not need to like create any separate objects. For example, in RabbitMQ library, they use these methods to schedule asynchronous work, because when you have like something like RabbitMQ, you need to do it very, very fast. So every performance optimization matters. But of course, for regular web APIs, we can just create tasks, regular tasks. This is not needed at all. And yeah. Let's talk a bit about advanced configuration. Now, there are a couple more topics about performance, but I guess I'll get back to them better on Friday to talk today also about configuration. So more advanced configuration options of all the primitives that we discussed so far. Let's start with cancellation. Cancellation token source, it also has a special method on the token. A cancellation token has a special method, register. This register method, it registers a delegate to be run whenever cancellation happens. So if somebody cancels later our cancellation token source, this method will also be called. here we call two methods, this one and this one. And this operation, TCS cancel, it will actually block the main thread until both of methods have run. So it will run them synchronously in the order in which they are registered and will wait until they are both executed. If you want to not block the main thread, you can use a new method that was added, I think, in .NET 6, cancel async, which will just await this operation of calling all these methods on the register. Also, register returns you a iDisposable. It returns cancellation token registration, which is iDisposable, and you can either using construction or calling manually dispose. You can dispose of it, and it will cancel this registration. So later, when you call cancel, it will not be called if you already dispose of it. Task has status, like we discussed before. Let's look at that. So it has a status created, waiting for activation and waiting to run. Task will be in one of these states whenever you just scheduled some work and it has not been yet scheduled on the thread pool. However, as soon as some thread of thread pool is available, it will pick up your work and your task will be transferred into running state. After your task is completed, it is transferred into run to completion, into cancelled, or into faulted state. Faulted means exception has been thrown inside it. Cancelled means task operation cancelled exception has been thrown inside it from some cancellation token. And run to completion means that it successfully completes. However, task has one more option that we did not discuss, waiting for children to complete. What does it mean, waiting for children to complete? Task can have child tasks. For example, here we create a new task with task run. And inside, we are sleeping for 1 second. And that's all. We do not do anything else. We just create 3 more tasks and we exit this method. However, when we create each of these tasks, we also specify task creation options attached to parent. Attached to parent means that this task is a child task to the parent task. And the parent task is the task that is currently executing this code. So it will be this task. So until any of the child tasks are not complete, parent task will also not complete. So initially, whenever this is executing, this task state is running. As soon as it executes this, it creates 3 tasks and then it exits. But it sees that it has 3 tasks attached to it as children. And it transfers not to completed state, but it transfers to waiting for children state. So it's now waiting for children to complete. After all these tasks are completed, only then this task is switched to completed state. So in this example, it's 1 second plus all these three tasks are waiting for 5 seconds. So in total, it will be 3 seconds. Let's run this example. Yeah, of course, I made some mess here and somewhere else. Let's run this example. Something else somewhere. What is? Let's run. Okay, let me just quickly. So here it's run for 1 second and then it completed. But why it completed? we thought that it's going to run for 6 seconds because it should wait for these tasks. Well, it's because task run is creating a task with pre-configured options. And if we create a task like this, task factory start new without any pre-configured options, then it will work. Let's check. 961 starts in a task. See, we are waiting for 6 seconds. Actually, if I pause it before it's completed, we can check that its status waiting for children to complete. So it's now waiting for these children. Why it didn't work with task run? Because whenever we create a task, we can also specify task creation options. Deny child at touch. Deny child at touch option means that this task should not allow any children to attach themselves like this to itself. And task run does just this. Task run has one option, deny child at touch. So whenever you create new tasks with task run, you can be sure that no other tasks inside it will be able to attach to your task and prolong its execution. So in this short example, we covered both attach to parent, deny child at touch, and also task status waiting for children. Now let's look at task schedulers. Whenever you create a new task, you can specify task creation options, which have different parameters like deny child attach or, on the contrary, attach to parent. And you can also specify a scheduler. A scheduler is a task scheduler class, and it denotes how your tasks are going to be scheduled on a thread pool, or maybe even not on a thread pool. This is an example of using some task schedulers that are predefined in .NET. In .NET, there is a class concurrent exclusive scheduler pair, where you can specify task scheduler, where I'm just specifying default task scheduler, the parent task scheduler that it will use for scheduling, and also max concurrency level, where I specify 3. And then this class has two properties, exclusive scheduler and concurrent scheduler. Exclusive scheduler will allow tasks to be executed only on a single thread, and concurrent scheduler will allow tasks to be executed only on this amount of threads, only on the 3 threads. So if I'm using concurrent scheduler here, these tasks will be able to run only 3 at a time. However, this is not a locking alternative. So if you need to make sure only one task is executing at a time, you need to use locking, semaphore slim or lock construction. You cannot use this exclusive scheduler because exclusive scheduler does not make sure that only one task executes at a time. It only makes sure that only one thread is executing at the time. So if your scheduler schedule 1000 tasks here, but all of them will just do task delay for 1 hour, they will all run instantly on this exclusive scheduler, and together all 1000 of them will start at the same time, because none of them will use any threads at all. And if some of your tasks are switching threads and use a bit of one thread and a bit of another and just then waiting and running something, then maybe you can have 80 different tasks executing interchangeably on this exclusive scheduler. The scheduler will only make sure that all different bits and pieces of your different tasks are executing on just one thread. But they can always, whenever one task is yielding to thread pool, so if there is an await construction there, any other task that is waiting to get executed by this thread can just be picked up by this thread. Now, in order to understand some of more options, let's quickly run through the internal implementation of thread pool. Thread pool has a global queue, so whenever you schedule a new task, it will be scheduled on a global queue. And every worker thread also has local queues. So if you schedule a new task from main thread of your console application, it will be scheduled on global queue. Some of the worker threads, for example, worker thread 2, it will see that it doesn't have any values in its local queue. It will go to the global queue and it will get your methods to be executed from the global queue. It gets this method to be executed and it starts executing it. If inside that method you have some more tasks to create, you're calling some async methods, you're waiting them, or you create new task run, then all these tasks will be allocated on this local queue of thread 2. So any other child tasks, they are allocated on internal local queue of the thread that is currently executing your code. Later, whenever any of other threads are waiting, for example, thread 1 and thread 2 and thread 3 are also waiting to execute some code. Any thread that is currently free, it constantly checks whether it has items in local queue first. So if it has items from local queue, it just takes them and executes them. If it doesn't have items in a local queue, then it first checks all the other local queues of other worker threads. So it will go and check if other local queues have any items. Local queue 2 has some items, so it will take it from local queue 2 to its own local queue and will execute it. However, if all the other local queues are also empty, only then worker thread 3 will go to the global queue and then it will get an item from global queue. This is done to avoid locking as much as possible because locking degrades performance. So this is a very performant way so that threads can execute items from only its local queue without any locking at all. If it needs, it goes and uses a lock from other queues one by one to check if they have any items and then it gets it from there. And only if there are no items, it goes to global queue and acquires a global lock. Whenever we create a task, we have these task creation options. Let's go through them. Task creation options, none is just if you do not specify anything. Then prefer fairness. Prefer fairness tells the task scheduler to schedule this task with, well, basically preferring fairness. So you want your task to be executed as fast as possible and as fair as possible. So it is more likely that your task will run sooner than later. Prefer fairness is basically schedules your task on the global queue. So instead of scheduling it on local queue. Long running is an option that you can specify to let the let.NET know that your task is long running. It will then provide a way to more aggressively create threads if you need them. For example, if you run into an issue that your thread pool is oversaturated or undersaturated. So you have some starvation issues, then this task might be still created fast because it is long-running task and needs to run for a long time anyway. Attach to parent is, attach to parent, deny child attaches, and denying attaching any other tasks to this parent task. Hide scheduler hides current scheduler from any child tasks. So if you have some custom scheduler, but you want any other child tasks created inside to use a default scheduler, you can use this option. And run continuation asynchronously was added pretty much mostly for a cancellation token source. Like I showed you an example, cancellation token source can introduce some deadlocks if you do not specify it here. Task creation options, run continuations asynchronously. it basically means that it will run them asynchronously. Now, whenever you have a task and you actually I have a separate example for that. Whenever you have a task and you use the method continue with, apart from task creation options for this continuation, you can also specify task continuation options. This is different options. It has all the same options, the task creation options. Also, it has a couple more options like lazy cancellation and a bunch of options to configure the flow of this continuation. So, for example, not run on completion will only run that continuation whenever task is failed with exception or has been cancelled. But if it is successful, it will not run it. Not unfolded, well, not when exception has been thrown, not uncancelled. It's understandable. Also, there is only uncancelled, only unfolded, and only on run to completion. What does lazy cancellation mean? Lazy cancellation, well, if you have a task and you configure it with continuation, and then you configure it with another continuation, for example, you do this. Something like this. Then this continuation will run even if, not like this, but probably like this. This both continuation will run when task is completed. But if the task is cancelled, then this continuation are not being run at all instantly. I also have an example for that. So we have a task 1, we have task 2, which is task 1 continue with, and task 3, which is actually task 2 continue with. So first this task is run. After this task is completed, then this task is run. And after this task is completed, then this task is run. However, if you have already cancelled, like I'm here canceling before even starting to wait for first task, so when the delay did not happen yet, let's make it shorter. I'm already cancelled this token. So if this token is cancelled, then the third continuation will not execute, even though we did not specify here only on completed, only on faulted, etc. It is because .NET sees that something has been cancelled and it cancels all the other cancellations down the chain, all the other continuations down the chain. In order to avoid it, we can specify lazy cancellation. It will mean that all the other continuations will be able to later check if it's cancelled or not and run if they are configured to run whenever it is already cancelled. Like here, we do not have any custom configuration, so it will run even if the previous task has been cancelled. But it will not run if we do not specify this lazy cancellation. Yeah, I still have a bunch of stuff here that I wanted to discuss, but I guess since it's already 3, let's let me just ask if anyone has any questions. Let's discuss the questions probably first, and maybe move everything else to Friday.
Actually, I have a question related to value task with your example when you fetch string value from the cache. Can you come back? Yes. I believe the main benefits here that there is a probability that we fetch value from the cache and we do not await. We do not await, and that is the main feature of value task. in other words, we have a hot path here. But let's imagine that we do not have a cache here and always make a request to external provider or database. Do we still have? Do we still should use value task string instead of just task string?
Well, good question. Thanks. In general, if you are sure that your await operation is working on a pure task that is implemented in the old way using just regular tasks, and you are sure that you are not going to change it in future, then yeah, there is no difference between using task and value task. You can just continue using tasks. It will not be any performance benefit to use value tasks there. However, first consideration is we are not calling databases or any other libraries manually, right? We're using different libraries. And some of these libraries are already seeing a tendency to convert to value tasks. So they might be using some optimized algorithms under the hood, like I showed in uh, in value task source example. This interface, it allows us to create completely asynchronous tasks that actually go to some external sources and receive some data, but they do not allocate any tasks. They are pure value tasks. So because of this magic thing, uh, we, we can actually create value tasks that are not being used just to return in synchronous value, but they are internally asynchronous, and at the same time, they are not allocating any tasks. So if you see that when you call your library, the library returns you a value task and not a task, then it will be beneficial, probably, again, based on the internal implementation of that value task, uh, it might be beneficial to also use value task around this value task. But if we use old-fashioned tasks, then yeah, most likely it will not bring any benefits.
Thank you. And there is another question regarding the value task. Somewhere I read, probably in the comment to pull request, that some people thought that value task is there are a lot of benefits when we use with together with value type. It means in case here we have a string. String it is reference type, but some people thought that in case it is, let's imagine that here we return value task int or GUID or datetime. In that case, I read it like advice that we should always use value task with value types in .NET. I mean int with structures. In that case, we have a lot of benefits. Can you somehow provide the comments regarding this?
Well, to be honest, I did not hear about this anywhere. So yeah, I will investigate it and maybe provide some information on Friday. But in general, I don't think there is any connection between value types and value tasks. Value task is just called value task because it is allocated on the stack instead of heap. And it provides for us a way to not allocate tasks. But I don't see how like returning here int instead of some custom class is better than just like with the same idea. I can just tell you that it is better to return int from a method than to return a custom class, right? Just because this int will be allocated on the stack and class will be allocated on the heap. So based on that, yeah, it's probably better to use value tasks with value types just because value types will not be allocated on the heap. So if you need to allocate everything on the stack, it will improve somewhat your performance. But I'm using value tasks a lot, and I always return here some classes, because classes usually contain my data. So I am not sure how much benefit it can bring in regards to asynchronously. So yeah, I can see how it is more beneficial based on just allocation, but I don't see the difference between returning value task or just like, yeah, I guess.
Okay, that's enough. Thank you.
Anyone else? All right, if no more questions, then thank you for joining. Let's see you on Friday, where we will badly try to talk about everything we have so far. Still to talk about, because I'm not sure we'll be on time, but anyway, yeah, let's try it. Thank you guys. See you on Friday.